we will continue with a session on infrastructure nudges, which was a work package that has been led, or is being, no, it has been led because it's closed already at IKA here. And I want to introduce my colleague Anna-Lena in the beginning, and she will present a measure to nudge drivers towards safer driving via the infrastructure and how this does work. Yeah, we're going to see this right now.
Yes, absolutely. Some switching roles from presenters with leading through today's meeting to being allowed to present the results of the infrastructure driver nudge. And if we go to the next slide, what we can see is what did we want to do with this measure in this work package here. And what our objective here was to nudge drivers towards adapting a safe speed and towards adopting a safe trajectory. And what this especially targets is habitual speeding. So as I introduced in the beginning, if you're going down a certain road and you might be going this very often, or you might be engaged in a task that, well, you're not paying 100% of your attention to the road, it could happen that you're driving faster than you intend to do, or that you're driving faster than is safe for the certain situation. So what we are trying to do with this, or what we did with this measure, was to provide nudging via the infrastructure at a set location. And here we detect and nudge only those drivers who are driving too fast. So only those drivers are being nudged that show an increased speed or a speed that is over a certain threshold, and only those, and then they can, well, they can make the decision freely if they want to follow this nudge, or if they want to adopt, or if they want to keep driving the way they are. So as in the simple sense of nudging, it is completely up to the driver to decide if they want to slow down or not. So if we go one slide further, here I have listed the approach that we took in this work package here, and we did that together with the Institute of Automotive Engineering, also here located at RWTH Aachen University, with Heijmans in the Netherlands, and BMW. And first, we derived the measures and selected the location for this. So we asked ourselves, how could we nudge drivers towards adopting a safe speed? What are the psychological, what is the basis there on the psychological side to nudge drivers towards this? And what would be an appropriate location? So we'll come to what that is in a bit. But then we conducted driving simulator studies here at our simulator at IKA. This was then added, or we added then a Monte Carlo simulation by BMW, which investigates the potential impact of the infrastructure nudge in terms of traffic safety, and also had the objective to provide information for the technical development of the infrastructure nudge. And then furthermore, of course, the technology itself had to be developed to fit for this nudging measure. So existing technologies came in, and were also, something new formed of what was available there and was developed anew. So we had the detection and intelligent vehicle data that was developed by ISAC here, and this then fed into the decision control logic and the lights that were developed and prepared by Heijmans in the Netherlands. After a successful development of both the measure and the technology behind that, we went into the field tests, and there we had the location for the field tests prepared by Heijmans as well. Started our quantitative and qualitative data collection, and then of course went into data analysis. And if you go, if you remain on the slide, you can see on the right at the top the driving simulator. Then in the middle there's an icon for the Monte Carlo simulator. On the bottom you can already see, spoiler for what the actual measure looks like in the field. So if we go now one slide further, you can see a motorway exit in Eindhoven in the Netherlands. So we chose this motorway exit. On the left you can see the top view, and in the middle you can see the view onto the motorway exit from a bridge that is just before this motorway exit going over the motorway. And for those of you who are familiar with the Eindhoven area, it is when you come from outside the city, it is a motorway going into the city center. So at the location where the motorway exit starts, people had to go down from 100 to 70 kilometers per hour, several meters before the exit. Within the exit, we have 70, And at the end of the exit, in the middle picture, you can see a very small car that is already in the exit. And very much at that position, we have a 50 km/h sign. So there, the speed limit changes to 50. And well, we chose this location because this is a location where speeding can happen habitually. And this also shows a higher probability for almost accidents or risky situations in general. People do know exit situations very well, but as you can see here on the picture, we have many trees around it, so obstructed view, and the curve is getting narrower and narrower. So you might, if you're not familiar with the exit, you might not be sure, you might not know that this curve is getting narrower. And when you are in the curve and realize that you might be too fast for this curve, you might get into a risky situation. Doesn't mean that you are, because, well, some people are of course familiar with this exit when they live in the area, but what we also have here are traffic lights at the end of the curve. So if you look at the picture on the far left, we are coming from the bottom and following that red line throughout that exit, and on the right side of that picture, where the red line ends, there we have a traffic light. And it could happen that, especially in rush hour situations, vehicles are queuing up at the traffic light. So we definitely don't want people driving too fast in this exit, especially if they're not paying too much attention to the speed they have in a motorway exit situation, which is a very familiar one. So this is a potentially dangerous location. Doesn't mean that accidents happen there that frequently. If we hear the siren, we have a fire station next door, so don't bother about that. But yeah, this is a potentially dangerous location where we wanted to nudge drivers towards the safer speed. And we took this motorway exit and put it into our driving simulator. So you can actually come to our driving simulator and drive in Eindhoven, which is quite fun when you then actually go to the real life location. So yeah, the colleagues and I have been driving the simulation for testing purposes and for just preparing the tests numerous times, and when you then finally get to the location, drive it in real life, that's quite surreal. So yeah. However, why did we know that this motorway location, a motorway exit, was a good location for our measure? And if we go to the next slide, we can. There was a baseline measurement that was conducted by ISAC, and we have 3 radars that was that were put up before any nudging measure was put into the road. And the 3 pictures to the right depict the speed that was measured at those 3 radar stations. And the first radar is not the most interesting one, but you can see there are people driving over 70. And to me personally, if I go to the Netherlands driving, I just stick very strictly to the speed limit, because it is so much more expensive than in Germany. And but not all people are, and not everyone might be as focused on the speed when they're driving there. So if you go look at the second and the third radar, you can see that the drivers, or the majority of drivers, is well above 50 km/h. So there's definitely the potential to nudge drivers down here. So into the derivation or the development of the measures, and if we have a look at the next slide, we ask ourselves, how can drivers be nudged towards reducing their speed in such a motorway exit situation? And if we click once more, we start with a free collection with everyone who was interested from the consortium and from the partners. And we collected possible and impossible nudging measures according to the design criteria developed in the integrated framework that was presented by Marianne Carlson earlier. And then we derived the expected behavior from these solutions that we found were like, okay, according to existing psychological principles as well, what kind of behavior do we expect? Well, then we had to go further and reduce this wide collection of potential measures to medium-term feasible technical solutions. So we wanted to test this in the simulator and then take exactly this measure and test it in the field, which is, well, what we did. But for that, we had to test something in the simulation that could actually be implemented in the field. We prioritized to be tested factors that we wanted to focus on, for example, color or movement of lights. Now I saw that. And then we prepared and conducted our simulator testing. And this is what I would like to come to next. So we put light stimuli on the exit lane that is on both sides of the road at road level. and those were only turned on, or those are supposed to be only turned on if the car is coming in too fast, and they are aiming and signaling to the driver that they are driving too fast, and should have a decelerating effect on the speeding driver. And on the right, you can see the lights. So in the simulated study, we had one light placed every 4 meters and had lights activated, and the distance between 2 activated lights was 20 meters. And these were either statically illuminated, so when a car came onto the motorway exit, they were turned on. Another condition was, of course, baseline, and another one was lights moving towards the driver, creating therefore an illusion of the driver driving faster than they actually are, because their surroundings are moving past them faster than they're usually used to at this speed. And then we also had a qualitative part of the study. And if we go further, you can see a bird's eye view of the location Eindhoven. So in the middle, you can see the exit. If we go one step further, we can see what it looked like in our simulation software. And if we have one step more, this is what the participants saw when they were in the middle of the exit. So right now you might think, well, that is not a very bright light, or that's very small stimulus. Yes, but you're seeing a very small picture. So imagine driving in that location, or in our simulator where you have 180 screens and further screens for the rear view. And the lights are also moving past you, and that creates a perception of speed there. Going further, what we found was velocity decreased earlier when the lights appeared on the road compared to no lights, and especially the lights moving towards the driver results in earlier reaction of the driver. One possible reason for this could be that there is a higher alertness of drivers because of this movement component, and we found this reference of lights moving towards the driver quantitatively and qualitatively. So both in the driving data and when we asked people. And we tested different colors, for example, green lights, amber lights, white lights, in a qualitative part of the study, and red lights were perceived as most effective. We wanted to go further and conduct a second simulated study on the impact on drivers' attention, and we used a secondary task here. And when drivers, while driving, do a secondary task, when they reduce their secondary task activity, you can this provides information on the focus of attention of the driver. So it's most likely that the attention shifts from the secondary task to the driving task, which is exactly what is written here in that second point. So if we go one step further, we again had our 3 light conditions, substituted static lights with blinking lights, and had 3 secondary task conditions with an auditory secondary task or also visual secondary task, just to have a look at different modalities here. And what we found was that performance in the visual secondary task was lower than for the auditory secondary task. So of course we need our eyes for driving, which is why we cannot look at the secondary task at the same time. And attention was drawn to the driving task when the lights were there compared to the baseline. So what we can actually see is that the lights draw the driver's attention to the driving task, and have them focus on where they are supposed to have the focus of attention in that situation. So we do have a speed decrease, and we do have a shift in the focus of attention. Going further, we had a test in Aachen for software development, especially for the technical development, which I indicated earlier was done by Isaac and Clement. And what you can see here are pictures of thermal imaging cameras. So in the field, the system is able to detect drivers that are going too fast, and turns the nudging system on only for those drivers who are speeding. And of course, we have aspects like data protection. And as you can see here, we are not able to distinguish any number plates, any people or car brands, colors, whatever. This is anonymous. And if we go one step further, I hope this video works for you. This is how the system detects the cars. There's a coordinate system, and then the able to transfer this to a database. And if we, I'll let that roll for a second until the video is finishing. So as you can see, this is a real-time processing, and the delay is minimal. Going one slide further, we can see that we then mounted the cameras, as you can see on the light, onto the motorway exit. And now you're coming from the top if you have a look at this picture here. And we have 4 cameras, 3 needed to detect the drivers, and we have a real-time detection. So when a driver comes into the motorway exit and is detected as driving too fast, the light system is turned on. If they slow down enough, the camera system, the decision control logic, detects that and turns off. If he speeds up again, it can be turned on again. And on the right, you can see the threshold that is put in between. We have drivers, when they are 10%, they will be nudged. And if they are below, they will not be nudged. And that decreases from the beginning of the motorway exit, where we have 70 kilometers per hour allowed, until just before the 50 kilometers per hour side, because we want to gradually nudge them down, that they have safe and slower speed when they are in the curve of this exit. Yes, we then went further, and you can see here how the lights were built into the road. So it was actually drilled in there, lots of cabling, and lots of on-site work by the colleagues of Heinz and Isaac as well to calibrate the camera. And yeah, we then had it established. And here you can see a video, and I really hope that this works without too much delay. But here you can see the lights moving towards the driver. And this was an early stage, so the pylons on the left are not there. On the right, you can see still see the building crew. And yeah, here you have an impression of the motorway exit. And if we go one slide further, we do have a top view from the bridge that I just indicated. And as you can see, the stimulus moves with a car. So we have a minimum distance between 2 cars following one another of 90 meters, because one car will be nudged by one that is just in front of it. But when we wanted to be able to nudge more than 1 car in the exit at once. Yeah, then we tested several scenarios in the field, and this is just a quick overview. But as you can see on the right, we had each scenario activated for a week, and there were almost 20,000 vehicles per week, if we have an overall look, and per nudging scenario that were driving through the exit. And yeah, if we look into the middle, we had different variations of how many lights are activated, static lights moving towards the driver, but as we found red as the most appropriate color in the simulator study, with a potentially greatest effect here, we put this into the field test. If we go one slide further, we also varied different light movement speeds, and what we also did was that we varied how many lights were activated at once. And still, we do have quite large sample sizes here. To show you an overall impression on what that looks like when we analyze the data, you can have a look at the next slide. And on the left, you can see the percentage of vehicles that are faster than the 85% wanted of speed in the baseline scenario. The baseline here is indicated with in black on the left side of the figure. And we see all the different scenarios, or the speed decrease, the deceleration in the other scenarios. And we could see a reduction of up to 39%, which was here for the scenario 4, which was static lights, so no movement component here. What we then can see on the right is we filtered our data set a bit, and this is one example of only those vehicles coming in between 80 and 85 kilometers per hour, which is the lower part of the speeding vehicle. But just to give you an impression, only if drivers are only slightly speeding, they're all slower than in the baseline. The baseline here is indicated in black. But what we can also see is we don't have a harsh braking event or drivers that are like hitting the brake and stopping. Well, these are averages, but we didn't see that in the data as well. Just to indicate, drivers do slow down, but they don't slow down like 20 or 30 kilometers per hour, but it's between 3 to 5 kilometers per hour. But that is enough if they are not driving too fast. We went into behavioral analysis, and if we have a look at the next slide, this is just an overview, and I'll just tell a few details. This is just testing phase 1 with 4 nudging scenarios with different variations in the baseline. And when we compare the stimulus onset and the position where the 50 km/h sign is, we do see a significant difference between the matching scenarios. And if we go into post hoc analysis, what I'm not going to bore you with today, we can actually see that we do have a decrease in speed, and especially static light scenarios, but also in some conditions, the lights moving towards the driver are very promising in slowing down drivers in a controlled way. We also ask people on site, if we go one slide further, online what they thought about the measure. This is just one example for the qualitative data collection that we did, and we were able together with our partners to distribute an online resident survey, and I already saw Milou on the line earlier who worked on this as well. And yeah, here we were able to distribute this questionnaire in the residential area around, and the general attitude of drivers was very positive towards the measure. Like, yes, I don't think it distracts me too much. It is good for drawing my attention to the driving task, and I think that the lights are suitable to decrease my my speed. And in both another on-site survey that we did, apart from this online resident survey, and in the simulator studies, we had it was, well, the same for all the data collections that we did. People liked the measure. They thought that it would work, which it did. Yeah, drivers actually thought that the lights moving towards them would work best to slow them down. Yeah. So if we go one slide further, there's just an example, and we asked them, if you could choose, which traffic measure would you use to reduce your driving speed? And they were asked to rank their reply. And in red here, you can see the first choice, and the highest proportion of first choices was the traffic sign, which is the 50 or 70 km/h sign, together with a light system. And they compared that to a traffic sign with a speed cam, which yeah, people accepted as well. And just the mere traffic sign without any intervention, which you could imagine it's the most familiar to people, did not have that much of a positive reply than the traffic sign with the light system here. To conclude my presentation, yeah, we saw in the field test after we had conducted our simulator studies in the Monte Carlo simulation to see what measure would be working, we saw that the infrastructure driver actually can reduce speed by approximately 5%, and it can also reduce the percentage of fast vehicles by up to 40%. When we look at especially fast drivers, so the chunk of very fast drivers that are over 90 km/h or even over 100 km/h, we can see that the faster they come in, the more they are nudged, and they always drop slower when the system was active on average. They were influenced most here by the static lights in the field test, but they also were influenced by the lights moving towards them, and especially the very fastest drivers, and when the lights were activated in sets of 2 lights and not just 1 light, as you can see on the picture on the right. Of course, research is never done. So future research should, for example, focus on replication of the results in various locations, in different weather conditions, with different groups of drivers, because here we're in a residential area. We could imagine that people are quite used to the exit, even though that's not a must, and because we have an anonymized data collection of the quantitative results, we cannot say that. But yeah, it could also be possible to transfer this principle to other means of application, so other behaviors than speed and other locations if needed. And we would also work, and that is probably a process that is never done, to refine the system further to see if we want to include different vehicle categories, variable speed thresholds as well, and yeah, as I said, weather conditions and different behaviors. And yeah, at the same time with this measure, we were able to nudge drivers towards adopting a safer speed, and with a safer speed, we always come to a safer trajectory as well, which is yeah, one more aspect to this measure. So with that, thank you.
Thank you, Anna-Lena, for this presentation.